In this video, we're going to calculate different types of limits. So let's start with a function that's a piecewise defined function. And in number one, we're not going to calculate a limit. We're just going to evaluate the function at different x values. So let's start with f of 2.1. So to evaluate the function at 2.1, well, 2.1 is not equal to 2. So we're just going to substitute into x squared plus 3. All right, so 2.1 squared is 4.1 plus 3, that's 7.41. All right, now let's calculate the function. Let's evaluate the function at 1.9. Notice we chose two values, one a little bit bigger than 2 and one a little bit smaller than 2. Okay, so let's see. Again, just substitute in, since 1.9 is not equal to 2, we just use this expression, substitute in 1.9 squared plus 3. Okay, so that's 3.61 plus 3, and we get 6.61. All right, so notice we got, when we substituted in a value bigger than 2, we got something a little bit bigger than 7. And when we substituted in something smaller than 2, we got something, a value that was a little bit smaller than 7. Okay. Now let's look at f of 2 itself. Well, according to these directions over here, f of 2 is equal to 10. When x equal 2, the function is equal to 10. So f of 2 is 10. In number 2, we're looking at the limit as x goes to minus 2 of this function. Well, this is a polynomial. X squared minus 3x plus 5 is a polynomial. So we know that the limit as x goes to any value of a polynomial is just obtained by substituting in that value. So since this is a polynomial, all we have to do is substitute in. So the limit as x goes to minus 2. All right, we just substitute in minus 2. So we have 4 plus 6 plus 5, and that's equal to 15. The limit is 15. Now we're looking at a limit of function as x goes to 2 of function f of x. Now f of x is not equal to a polynomial, but it is equal to a polynomial everywhere except at the value x equal 2. So f of x is a function that is equal to a polynomial except at a finite number of points. In this case, except at only one point. So we have the following theorem, similar to what we used in the previous problem. In the previous problem, we said if our function is a polynomial, when we take a limit, we can just substitute in. So here, when our function is almost a polynomial, I'll call this almost a polynomial, the same thing. We can just substitute into the polynomial. So here's what we're using. If f of x is equal to a polynomial everywhere except at a finite number of points, then when we take the limit as x goes to any value at all, again, we just substitute in. But where do we substitute in? We substitute into the polynomial, not into f, but into the polynomial. In other words, for the sake of finding limits, we're only going to use x squared plus 3. This value 10 does not enter into the calculation. So the limit as x goes to 2 of f of x is equal to the limit as x goes to 2 of x squared plus 3. In other words, now we can just substitute in. All right, so that's 7. So it really, this value 10 did not enter into the calculation. Now, remember the previous example where we just evaluated this same function at these two x values, 2.1 and 1.9, and we did find that f of 2.1 that was equal to, this was 7.41, and f of 1.9 we got 6.61. So the value of the function at evaluated close to 2 was close to 7. So that's why it makes sense that the limit as x approaches 2 should be equal to 7. If you substitute in values close to 2, you get values close to 7. Not close to 10, close to 7. All right, so that's why it makes sense that the limit should be 7. Okay, so it really doesn't matter what number this was over here. So here we have the first example of a function where the limit is not equal to, let's write that this is not equal to f of 2. Okay, because f of 2 is 10. In number 4, we're taking the limit as x goes to 3 of the square root of x squared minus 5. So we're going to look at this as a composite. We're going to think of it as a composite function, where the outer function is the square root function and the inner function is the polynomial x squared minus 5. So we have the following theorem. When we take the limit of a composite function, we can just take the limit of the inner function. All right, so that's what we're going to do here. We're going to just take the limit of the square root. We're going to bring the limit on the inside, so we're going to take the square root of the limit of x squared minus 5. So in other words, applying this theorem to our function, we say that the limit as x goes to 3 of the square root of x squared minus 5. So our outer function f is a square root function, so we're just going to put that on the outside and put that square root on the inside. Now this then is a polynomial. X squared minus 5 is a polynomial, so we take the square root just by substituting in. All right, so we're just going to substitute in underneath that square root. So we have 3 squared minus 5, 9 minus 5. So that is the square root of 4, or 2. Again, we just basically just substituted in this case. In number 5, we have a rational function. And again, we're just going to substitute in because we have the following rule. The limit as x goes to c of a rational function, let's call it p of x over q of x, is equal to, in other words, we can just, is equal to p of c over q of c. Just substitute in if c doesn't make the denominator 0. C is not a 0 of q of x. So that's the situation we're in here. If we substitute 2 into x squared minus 9, we get 4 minus 9, which is not equal to 0. So again, just substitute in. That's what our rule tells us, that in this case, we could just substitute in. So let's do that. So we have 2 minus 5 over 4 minus 9 minus 3 minus 5, so that's 3/5. In number 6, we again have a rational function. However, 5 is a 0 of the denominator. If we substitute 5 in, we get 25 minus 15, which is 10, minus 10, which is 0. So in this case, we can't just substitute in. However, we have the following rule. Okay, that the limit as x goes to c of a rational function what we could do is we could just reduce, and then if after reducing, if c is no longer a 0 of the denominator, then we could substitute in. So we could say that this is equal to the limit as x goes to c of, let's say, the reduced is p of x over q of x, but this time reduced. So in other words, reduce first and then try substituting in. So in this case, so let's do that here. Let's try that and see if reducing eliminates that 0 from the denominator. All right, in order to reduce, we're going to factor x squared minus 3x minus 10. So let's do that. All right, so this factors into x minus 5x plus 2, and that's convenient because now the x minus 5 will cancel with an x minus 5 in the numerator. All right, so this is the reduced version is right here, 1 over x plus 2. That's reduced. So now we can take the limit by just substituting it in, because now 5 is not a 0 of the reduced fraction. It's not a 0 of the denominator of the reduced fraction. So now we can just substitute in. All right, so just to summarize, if c, let's say, is a 0 of the denominator, try reducing first. Okay, that's basically what we're doing. Okay, number 7 is similar to number 6 in that we can't substitute 4 in because 4 is a 0 of the denominator. Notice that 4 is also a 0 of the numerator. When we're in that situation, we can also often do some canceling. Let's see, if we substitute 4 into the numerator, we have square root 9 minus 3, which is 3 minus 3, 0. So when we're in the situation where we're taking a limit and let's say as x goes to 4, and 4 is a 0 of both the numerator and the denominator, very often we can do some canceling. But in this case, we don't see how to factor out x minus 4 from the numerator like we did in the previous example. Okay. So we're going to have to do a little bit of manipulating. All right, and we're going to just apply a standard trick. All right, so what we have in the numerator is an expression that is the difference of a radical and a number. So it's a difference involving a radical. In order to manipulate expressions like this, what we do sometimes is we multiply top and bottom by the conjugate of that expression. So that will get rid of the radical, and sometimes that helps in simplifying the quotient. So this is a standard trick. Now the conjugate would be the same expression, but instead of a minus subtraction in the middle, we have an addition. Now we have to multiply in order not to change the in order to get an equivalent expression, we have to multiply numerator and denominator by the same expression. So we multiply numerator and denominator by the conjugate. All right, so let's do that. What we're hoping is that an x minus 4 will appear in the numerator. Alright, so let's do that. Multiply. We're foiling this out. So here we have square root times square root, we just get x plus 5. Now for the outer, we have 3 times the square root, and for the inner, we have minus 3 times the square root, and they cancel each other out. That's what happens when you multiply conjugates. So let's do last times less, and we have minus 9. In the denominator, let's not FOIL this. Let's just write x minus 4 times square root x plus 5 plus 3. We don't want to FOIL it out because we want to cancel x minus 4, so keep it as x minus 4. Now notice in the numerator we have x plus 5 minus 9. That is equal to x minus 4. So that's what we were hoping for. We were hoping that this manipulation would give us an x minus 4 in the numerator. Alright, so now we can cancel this x minus 4 with this x minus 4. Let me just write limit in front here. Limit x goes to 4. Alright, so now we can cancel this x minus 4 with this x minus 4. So we are left with the limit as x goes to 4 of 1 over square root x plus 5 plus 3. Now 4 is not a 0 of this denominator, so now we can just substitute in 4. So let's do that. Okay, so that's equal to, now we're actually taking the limit, so I dropped this limit notation. Okay, so this is substituting in 4. We have 1 over square root of 9 plus 3. That's 3 plus 3, or 1/6. So the limit is 1 over 6.